Okay, so I'm going to go through example 3 from the PowerPoint, but first I wanted to review the basic premise because this is really at the root of all the calculations that we're doing with ionization. So the first example we're going to look at is phenylbutazone, which is a weak acid. The basic premise that weak acids will ionize in an alkaline or basic environment, weak bases will ionize in an acidic environment, and that the ionized particles can't cross membranes very easily. They'll be relatively trapped. So the non-ionized form is what can cross membranes and move more freely. So if we take our first example that's going to be a weak acid, what we know is that if we put this weak acid into an acidic environment where the pH is low, let's just say pH of 1 to represent a low pH, then if we put that weak acid in there, it's going to be predominantly in the non-ionized state. So the proportion of non-ionized particles will greatly outnumber the ionized particles. Likewise, if we put that weak acid into a more alkaline environment, a more basic pH, let's go up here and say pH of 13, really high, then we know if we put the weak acid in an alkaline environment, it will become very ionized. So the ionized particles will greatly outnumber the non-ionized particles. But what is an acidic environment? pH 1 is pretty much universally acidic, but up to what level? What is an alkaline environment? And a lot of times people will say, oh, above or below 7, because that's kind of what we're trained to, because water is neutral. But in this situation, remember what we're saying is the environment in which the direction is going to favor, in the acidic side of things, favor this moving into a non-ionized state. And once we start to get into an alkaline environment, we're going to favor the ionized state. So what we're really talking about is either side of the pH at which the non-ionized and ionized are perfectly equivalent. We know what that is. That is the pH that equals the pKa by definition. So when the pH of the environment equals the pKa of the drug, we know that our non-ionized and ionized particles will be in equilibrium, and it's going to be 1 to 1. 50% non-ionized, 50% ionized, a 1 to 1 ratio. So therefore, when we say if we put this weak acid into an acidic environment, what we're really saying is if the pH is any lower than the pKa, then it's not going to be 50-50 anymore. What we're going to see is as the pH drops, the non-ionized form will predominate. So we'll have a 10 to 1 ratio of non-ionized to ionized, 100 to 1, 1,000 to 1. And likewise, as the pH of the environment rises above the pKa of that drug, we're going to see the ionized form predominate. So we'll have maybe a 1 to 10 non-ionized to ionized, 1 to 100, 1 to 1,000, as the pH gets further and further away from the pKa. Now, if we were to look at a weak base, we're basically doing the same thing in reverse. So let's say instead the drug that we're dealing with is a weak base. If that's the case, then we know what's going to happen in a relatively acidic environment is going to tend to ionize, so the I will be greater than the N. So what we're saying is that when the pH equals the pKa, the N to I ratio will be 1 to 1. They're evenly balanced, 50% of each. And as the pH decreases lower and lower than that pKa, we're going to see a skew toward ionization. So for every 1 non-ionized, there'll be 10 ionized, 1 to 100, 1 to 1,000. And likewise, as the pH rises above that pKa, we know that putting a weak base in a more alkaline or more basic environment, it will be more and more non-ionized. The non-ionized form will predominate. And so as the pH rises, we're going to have 10 non-ionized for every ionized, 100 to 1, 1,000 to 1. And this is just a visual way or a way of relating these basic behaviors of our weak acids and weak bases to the calculations that we're going to be doing. So going back to our example 3, we had phenylbutazone, which is a weak acid with a pKa of 4.4. And we want to know how is this drug going to behave if we put it into the stomach lumen with a pH of 1.4 when it comes in contact with plasma with a pH of 7.4. So same idea. We have now a drug with a specific pKa, and if we're in a more acidic environment, so our drug's pKa is 4.4. We know at pH 4.4, our N to I ratio is going to be 1 to 1. So if the pH goes any lower than 4.4, this is a weak acid. In an acidic environment, it will be more non-ionized, so our N will be bigger. And if we put this into a more alkaline or more basic environment, the pH goes higher, then our ionized form is going to predominate. So that's sort of our basic premise that we're working with. And just based on that, you could probably figure this question out. But let's look at it with the calculations. So in our GI lumen, we have a pH 1.4. And in our plasma, pH 7.4. So the first step before we can compare the two is figuring out what will this drug do in each of these compartments. So in the pH 1.4, we can use our 10 to the pKa minus pH equals, because this is a weak acid and N is high, will equal N over I. And if we do that on this side, we've got 10 to the 4.4 minus 1.4 equals N over I. So 10 to the 3 equals N over I. 1,000 over 1 equals N over I. So the important thing here is to keep in mind that this means that there's 1,000 N's for every one I. I should make my eyes like that. I'd also point out that, this is that an I. This is the same as if we said 2,000 over 2. It's the same as if we said 500, not 5,000, 500 over 0.5. These are all equivalent fractions. The relationship of N to I is preserved. So we have that. Now on the other side, our other compartment, we have a plasma pH of 4. So 10 to the 4.4 minus 7.4, is that what I said, equals N over I. So in this case, 10 to the negative 3 equals N over I. And the way that I gave this in my examples is to say 0.001 over 1. Now, some of you may be more used to saying N over I equals 1 over 1,000. And again, I'd like to point out that 0.001 over 1 is the same as 1 over 1,000. It's the same as 2 over 2,000. These are all interchangeable equivalent fractions. We're just talking about the ratio of the numerator to the denominator. And so as long as you keep your N's and your I's straight, it doesn't matter what you use. The reason that I give it in this format is if you don't know this and you type 10 to the exponent negative 3 in your calculator, you're going to get 0.001. So you can just put 0.001 over 1 and you're going to be in the right path. So let's just stick with that for now, the 0.001 version. So on this side we have N over I equals 0.001 over 1. Just clear some of this stuff away. So now that's sort of step one. We know how the drug is going to distribute itself in each of these two compartments, if that was the only compartment we were considering. But now we want to say, well, what's going to happen if we put a membrane between these two pH fluids and see where the drug decides to go. And so when we're doing this, what we're going to do is set the N's equal to 1. But the reason that we're doing that is, again, if you think on this side, you've got N's and I's in an equilibrium. And we said that for every 1,000 N, there was 1 I. And then on this side, on the plasma side, N's and I's are resting in equilibrium. On this side, we have 0.001 N to every 1 I. So if we looked at each one separately, that's how they'd orient themselves. These I's they can't cross the membrane. They're trapped there. So they're not really able to do much. They're not determining factors in this. The ends, on the other hand, these guys can cross freely. So what's going to happen is that these are going to try to equilibrate with each other. Are they at equilibrium right now? We've got 1,000 particles on that side and less than 1 on this side, nowhere near equilibrium. And so this is not our final state, or this at least doesn't represent what's going to happen. We can't use these numbers directly. So if we were to imagine that it was like this, this 1,000 particles would try to distribute. So we might have 500 on this side, 500 on this side. But as soon as some of these leave over here, remember there's a strong drive for them to move toward non-ionized on this side. So some of these would become non-ionized. This would actually be 0.5. And over here, the same idea. The drive is for this to be 0.001 to 1 ratio. So we would end up with a much larger number ionized. As soon as these guys get over here, they're going to ionize. So that kind of thing would keep happening, and we could sort of draw it out and see what it is. But ultimately, the point is that at the end of the day, oh, wow, I went too far. At the end of the day, we can simulate reaching equilibrium by making these ends equal to each other. What we do by convention is just set n equal to 1 on both sides. It doesn't have to be. We could have n be 1,000 on both sides. We could have n equal 0.001 on both sides. Just by making the ends equal, we're saying, okay, this is the point at which the ends have equilibrated with each other. If we set them equal to 1 on each side, we still have to maintain this relationship between n and I. So if 1,000 n's gives you 1 I, then if you have 1 n, you need to have 0.001 I. So you could say, 1,000 over 1 equals 1 over x. You could cross multiply. You could divide top and bottom each by 1,000. Whatever system you use to convert those, just recognize that they're equivalent ratios. The relationship between n and I is not changed. But now our n is set to 1. Likewise on this side, if we had 1 n, if we want to maintain this relationship that is going to be driven by the pH of 7.4, then it's going to be 1 n for every 1,000 I. And again, 0.001 over 1 is the same as 1 over 1,000. It's the same as 2 over 2,000 and any other variation you can make. So we're basically just choosing the ratio or the fraction in which our n happens to equal 1, because now our n's are equal. We know that we've reached equilibrium. When the n's have equilibrated, we know that for every 1 n on the GI side, on the gastric lumen side, there's going to be a tiny, tiny fraction of an I. For every 1 n on the plasma side, there's going to be 1,000 I's. So now that we're at equilibrium, we can take this a step further. And at this point, what we're dealing with is 1 non-ionized particle over here plus 0.001 ionized particle over here plus 1 non-ionized particle on this side plus 1,000 ionized particles on this side. Now realistically, this 0.001 is pretty negligible. It's not really contributing much. So most of our particles at any given moment in time are distributed between these 3 states. And so we're really dealing with a total, components, total number of particles of 1,002. This is just, again, relative proportions. We could say what proportion of particles is in the non-ionized state on the plasma side of this equation at any given time. Well, it's going to, at any given time, 1 part is in that state versus 1 part in this state and 1,000 parts in that state. So 1 out of a total of 1,002. But that's not really clinically useful for us. Honestly, once we get to this stage of things and we have defined what proportion will be in each of these 4 states, the only thing we usually are interested in is what's the total number, ionized plus non-ionized, in the GI compartment. and what's the total number, non-ionized plus ionized, in the plasma compartment. And so if we do that, the total number in our pH compartment is about 1, is technically 1.001. And the total number in our plasma compartment is 1,001. Remember, we have 1,002, and if you want to be technical, 1,002.001 in each. So now if we want to say what percentage are in this compartment, is going to be 1 divided by 1,002, because now we're just talking particles. We don't have to keep n's and i's separate. If we wanted to know what percentage is in this, it's going to be 1,001 divided by 1,002. But effectively, we're greater than 99% of our drug at this point is in this compartment. So if we had plopped the drug in here, held these two compartments, let them reach equilibrium, the drug is basically going to, on the GI side, be driven into the more non-ionized state. In that non-ionized state, it can cross the membrane, and as soon as it crosses over into this high pH, it's going to drive it into the ionized state where it's trapped and it can't bounce back. So there's this net flow going from the non-ionized to ionized. And so then the question, does that make sense? Does that match? Well, if you think about it in very, very basic terms, if we have this weak acid drug, if it was put into this relatively more acidic GI environment with a pH of 1.4, we know it's mostly in the non-ionized state, and that can move. And as soon as it crosses over the membrane into this pH 7.4, very alkaline, it's going to become ionized, and it'll be trapped. So there's always going to be a net movement from like to unlike, from the non-ionized state to the ionized state based on the pH. So the next example will be a little bit different, but hopefully this has clarified some things, and I will record example 4 if you need to look at it further. Thanks.